Okay, welcome back to our class. We had begun looking at elliptic curves, so we continue with that. Today, I want to see how to add elliptic curves using a formula, as I had promised. But before that, just to remind us what we did last time, we knew we learned about elliptic curves and, of course, their users. And then on addition of elliptic curves, of points on elliptic curves, we added using graphs. For instance, if you given point P and point Q, which are different, we said that then we would draw a line through these 2 points, a straight line, and this straight line will cut the elliptic curve at another point. It will cut it another point. Let's say maybe it cuts it this other point. This is our third point. Of course, then any straight line drawn to the elliptic curve through 2 points, through 2 different points, that line can only cut the elliptic curve at one extra point, not several points. So if the elliptic curve is something like that, and supposing this is the x-axis, cutting this elliptic curve into 2 equal parts. So if we have another point here and another point here, if you have to draw a line through them, this line will cut this elliptic curve at only 1 point, one extra point, not at 2 points. Now, once it cuts this elliptic curve at this extra point, we are to drop a perpendicular line through the x-axis to get the reflection of this point, or you can say the inverse of this point. So if this point is R, we're getting the inverse of R, and this becomes the sum of P plus Q. So it's just the inverse of R. Now, that is if you're given 2 points which are not equal and they do not lie on the same vertical line. Now, if it's the same point, P and P, adding them to get it to P, we say that what we will do, if this is our P, we would then draw a tangent line, a line passing, cutting this curve at only 1 point. We draw a tangent line through this point. So it touches this curve at this point this way, then extend it to cut the elliptic curve. Again, it will cut the elliptic curve at only 1 point. This point, we want to call it R, then reflect it through the x-axis. This is our x-axis, reflected through the x-axis. So just drawing a perpendicular line through the x-axis. Where it touches the curve on the other side, this is the inverse of R. And therefore, this becomes the sum of P plus P. If you want to get 4P, you would, this is our 2P, our 2P is here. You would again draw a tangent line. Of course, it will cut the curve, it will touch the curve only here, then extend it to cut. I've not drawn it properly. This one is not properly drawn because I know once you draw this tangent, it's supposed to cut this graph at only 1 point. So it touches it at R inverse, touches the curve at that point, and then extend it to cut the curve. It will cut it at only 1 point. So this one I've not drawn properly because you can see it's going to cut it here and then cut it here. I've not drawn it properly. But if you are drawing, constructing, then you would find out that it will only cut at 1 point. Then once it cuts again, supposing this is the only 1 point, this, you drop it. What we are doing here, we are reflecting it, drawing a perpendicular line through the x-axis. This point, this reflected point becomes 4P. The sum of, So this is what we call doubling of points. It is the equivalent of successive multiplication that we used to do with the real numbers, or a fast powering algorithm that we looked at. This is the equivalent. Now, so today we want to do the same thing. We want to add these points, but not by constructing them, but by use of formula. So, you know, when you are drawing those lines, we're coming up with a gradient line. So that gradient line is what we want to come up with and use it to add these points. Now, so my formula is here. The formula that we'll be using, I've said, supposing that this is our elliptic curve, and suppose we are given these 2 points, which are not similar, at different points, x1, y1, x2, y2. Now, so of course, we know that since these points are not the same, the gradient, the change in y over change in x gradient, which we usually say change in y, dy dx, change in y over change in x, would be y2 minus y1, y2 minus y1 out of x2 over x1. This is how we find the gradient. So I've denoted by S, I've denoted the gradient by S. So our gradient given by S will be change in y over change in x. Now, so we've already said that we have this curve, and you have this x-axis, and you have the 2 points, 2 points P and Q, for instance. So we've just found the gradient of this line. Just found the gradient of this line. Then it goes and cuts the curve at another point. Then we reflect this point. I will reflect it through the x-axis to get the inverse of r. This is our r. So that's what we want to do. We've already gotten the gradient of the line. Now, how do we get the coordinate of this point we are looking for? The coordinate of this point. This point, let's call it x3, y3. Let's call it x3, y3. So how do we get x3? Of course, you see what we did? We drew a line, then came, touch this, and then came back here. So this is what we have. So to get x3, the formula is you take the gradient, square it, then minus x1 minus x2. So just took the gradient, squared it, then subtracted x1, then subtracted x2. X1 was the x value for P, and y2 was the x2 was the x value for Q. So that's what we do. That's how we get x3. Now, after getting x3, you can now get y3. You can now get y3 after getting x3, getting y3. How do you get y3? Y3 is S multiplied by x1 minus x2, close the bracket, then subtract y1. Subtract y1. That's how we do it. So those are the formulas we use. And again, if you are writing a program, then you give it that formula. Give it the formula to give you the value of x3, and you give it the formula to give you the value of y3. If you're writing a program to assist you sum the points of the elliptic curve, then you're using this formula. You're giving it the formula to get y3, x3, and then y3. And of course, you've already given it this formula. You've already told it that if you're given 2 points P and Q, first of all, find their gradient. First of all, find the gradient of this and the gradient of the line that passes through these points. And the gradient is given by this. So you have given your program the the information that it has supposed to find the gradient. And after finding the gradient, it now proceeds to find x3. And x3 will be given by gradient square minus x1 minus x2. Then what about y3? Y3 will be gradient multiplied by the difference between, or this is x1 minus x3. X3, we've just gotten it from here. Just gotten it from here. So you put it here, then subtract y. Now, that is if the 2 points are different and if they don't lie on the same vertical line. Of course, if they lie on the same vertical line, then their sum is infinity. They give you identity. The identity we said is the point at infinity. So if you add them, if they lie on the same vertical line, so these formulas, it does not relate if points lie on the same vertical line. Now, if it's the same point, what did we say? Want to add the same point P to itself. Want to add P to itself. This is our x-axis. We said we would draw a tangent line through this point, touching the curve at that point. Then this tangent line extended to intersect our curve. Then we would then draw perpendicular or reflect it through the x-axis. That's the perpendicular line, perpendicular bisector of the x-axis. Now, this is the point we are looking for. This is the sum of P plus P. Want to call it X3, Y3. You notice that if this is our P, you notice that we cannot use the knowledge of the gradient we've used here. We cannot use this knowledge of this gradient because we'll be doing division by 0. Of course, we'll be talking of y1 minus y1, the same thing. But now the problem is not even the numerator. The problem is the denominator. The denominator will be giving us 0. So you cannot divide anything by 0. You cannot divide anything by 0. So that is, in fact, the problem is not in the numerator. When finding the gradient, you realize that the denominator will be having a 0. And so that is not possible. You cannot do that. And so how do you find gradient? The same point, using the same point, we are adding P to itself. This is how we get the gradient. We just use implicit differentiation that we talked about yesterday. This, when you do differentiation to this is the equation of the curve. This is the equation of the curve. So how do you differentiate this? You do it 2y dy dx. That is, you do this part is differentiated as 2y dy dx. But now the right side, you drop that, it becomes 3x squared. And then this one is just a plus a. The derivative of the constant is 0. So when you divide both sides by 2y, you find that dy dx is 3x squared plus a out of 2y. So this is what we use to find the gradient of the same point. When you are adding the same point to itself, adding the same point, a point to itself. So that is how we'll be using getting the gradient, but not the earlier method in part 1 above. The earlier method there, the denominator will be 0, and so that will not be possible. Now, so we've now obtained our gradient. Since we obtained our gradient, we find our x3 the same way we did here. The same way we did. The only difference is that x1 and x2 are equal in this case now. X1 and x2 are the same. So fact, we should have said x, this is gradient square minus x1 minus x1, because x1 and x2 are the same in this case. And so this is what gives us 2xy, x1. What about this? Again, we do it the same way we did, just the same way we did there. x1 minus x3 minus y1. So these formulas are just the same. The only difference is in determining the gradient. When you are adding a point to itself, the gradient, the way you determine it is slightly different from when you're adding two distinct points. Now, so those are the formula. So we want to take a few examples just to ensure that the formulas, we understand the formulas. And of course, we said when you're writing a program, then you just give the program those formulas, and it will do that for you. I've been given 2 points here. These 2 points are different. And I've noticed that they don't lie on the same vertical line. You can see the vertical line for this is this, and the vertical line for this is y is equals to 2, y is equals to 0. So they're not the same vertical line. So therefore, and again, they're different. So we use the first formula. And what does it say? That S would be y2 minus y1 over x2 minus x1. So then this is -2 out of 1, which is -2. That is our gradient. After getting our gradient, we go straight to find our x2, x3. And x3 is, it said, we take the gradient and then square it, then subtract x1, then subtract x2. So in this case, our gradient is this. When you square it, you get 4. And then subtract from it x1. x1 is -1. And x2 is 0. So this is same as 5. Because negative and negative will be positive. So x3 is 5. x3 is 5. Now after getting x3, you proceed and get y3. y3 is given by our gradient into x1 minus x3, then minus y1. Now, there's no problem which one you call x1 or x2. There's no problem. You can interchange. There's no problem. So this then becomes, what is this? This was -2. Now, but you must be consistent. Whether you interchange, but you must be consistent when you're interchanging. x1, we've been using x1 as -1. And x3 just obtained it as 5. Then if x1 is -1, then y1 should be 2. And so this gives you -2 into -6, then -2, which is 12 minus 2, which is 10. So that's how you get y2. And I've said you can interchange these things, but when you interchange, you ensure that you're consistent with your x1, y1, x2, and y2. But there's no problem. You can interchange, but you be consistent with your variables. Now, for instance, in this case, we used this as 0.2 and this as 0.1. You can interchange and call this 0.1, 2, and this 0.1 interchange. So that means if that is the case, then our gradient will begin by 2 minus 0 over -1 minus 0 again, which is -2. So there's no problem, just interchange. Then what about x3? Becomes this gradient square Then minus x1. This time x1 has been 0. X1 has been 0, and x2, no, 0, and x2 has been -1. So this is the same as 4 plus 1, which is 5. So I said it must be consistent. So that means, again, while getting y3, again, you must be consistent. It's S into x1. So this case, we've used x1 to be 0. Then minus x3. What about y1? Y1 will now be 0. Y1 will now be 0. And so this is -2 into -5, which is 10. So you can interchange these points, but what we are saying is every time you're doing that, you should be consistent with the values. Now, so we've just seen how to add 2 points, and we've added them. Of course, the formula is known to us. Let's again try this. Oh, this one, it says we go further and do that. Okay. And in fact, when you realize that, these are the same questions we did using graphs. These are the same questions we did using graphs, but this time just using formulas. Our gradient, so let's call this point 2 and this point 1. Let's call this point 2 and this point 1. So our gradient S is y2 minus y1, x2 minus x1. What is that? Y2 is -3, and x1, no, y2, y1 is 3. And then x2 is 0, and y1, no, x1 is 2. So this is -6 out of -2, which is then 3. Now, once we're done with that, we can find x3 now. And the formula says we take gradient and square it. Then from it, subtract x1, and then subtract x2. The gradient is 3, square it, you have 9. X1, we've been using 2. And x2, we've been using 0. Is it? This gives you 7. That gives you 7 for x3. What about y3? Y3, the formula is gradient x1 minus x3, then minus y1. What is our gradient? Is 3. X1, we've been using 2, and x3, we've just obtained 7. Y1 was 3. So this bracket gives you -5. Multiplied by this, you have -15. Then minus this, you have -18. This is our y3. So that means we've added a plus b. A plus b, therefore, is the point x3, which is 7, and y3, which is -18. This is the new point. That is our new point. Now, so we know that when we do associativity, the point we get must also be on the graph. That is what the question is saying. Now add a to this sum. Add a to this sum. A is still here. A is still there. And the sum we've just obtained, which we now call C, is the 0.7 negative 18 we've just obtained. These points again are not on the same vertical line. And I want to call this 0.2, and this is 0.1. So y2 therefore is negative 18, and y1 is 3. X2 therefore is 7, x1 is 5. This is negative 21 out of 5. That is the gradient I was getting. What about x3? X3 will be the gradient square minus x1, which is 2, then minus x2, which is 7. And that gives you this when you simplify. What about y3? Y3 will be the gradient into x1 minus x3. X1 minus x3, then minus y1. Minus y1. When you use your calculator, you get what I was getting. And therefore, the new point is 216 out of 25 and 216 out of, this is 3. This is 3111 out of 125. This is the new point. The sum of this gives you that point. Now, so the thing here is just knowing the formula for doing this and then employing that formula. Just knowing the formula and then employing the formula, that is the thing. And the thing again is that so that when we write a program, we know the formula we are giving it. Of course, I discover that sometimes when you write these programs, it's good to verify that your formula is working by doing it manually. We do it manually and then compare. If they accept, if they agree. Sometimes the program could be giving wrong results because of a slight error somewhere. So you need to know how to do it also manually so that you can compare your result. And if it's correct, then you can use program for larger values. Now, so this time I want to show you how to add a point to itself. I've been given A and I've been given B. I want 2A and I want 2B. Of course, this is the same point. So A and A is the same point, B and B is the same point. So then the formula for the gradient is 3x squared plus A out of 2y1. This is our S. So our point is 1, 1. So therefore, what is this gradient? Now, our point A is this 1, 2. So therefore, it's 3 multiplied by x squared, then plus A. A is from here. This is our A. This is our A. This is our elliptic curve. Our elliptic curve is of the form y squared is x cubed plus 2 plus ax plus b. So our A is -7. Our A is -7. Then out of 2, y is 2. Y is 2. It is 2y1. So this gives you 3 minus 7 out of 4. which is -1. Remember, our A is from the curve. That's where you get A from. So we've gotten our gradient. Now we proceed to find x3. And x3 by the formula is gradient square minus x1 minus x1 was the same point. And gradient square is 1, x1 is 1, another x1 is 1. So what we then get is -1. That is our x3. What about y3? The formula says should be gradient into x1 minus x3, then minus y1, minus y1. The gradient is -1. What about x1? x1 is 1. x3 just obtained it as -1 also. Then minus y1, which is 2. So the bracket gives us 2. Then there's a negative outside, it becomes -2. Then minus this 2, you have 4, negative. So because this is 2, inside the bracket is 2. 2 times -1 would be -2. Then minus that 2 gives you -4. So that means the coordinate, the new coordinate, when you add A plus A, that new coordinate is x, -1, which is the x3 value, and the -4, which is the y3 value. You can now get 2B before you go to the program, just to see how our formulas look there, how they are there, and how they then give us the results. The good thing is that this topic is it does not require any prerequisite. You don't require any other knowledge to learn this. It depends. It just does not depend on another topic to learn it. It doesn't require any previous knowledge to learn it. Let's add B to itself. Again, the gradient then will be given by 3x squared plus A divided by 2y. We're looking at point B. So that is 3. X is 3. Then plus A is coming from the graph, which is -7, minus 2y, and y is 4. Y is 4. So the first point here is 9 times that, which is 27. Then minus this would be 20. 20 out of 2 times 4. 4 will go here 5 times. And you have 5 out of 2. So this is our S. Then you get x3. x3 is gradient minus x1 minus x1. And gradient is 5, no, it's gradient square. Gradient square. Gradient square is that What about x1? X1 is 3 and another 3, so that is the same as 2, 3. Minus 3 minus 3 is the same as minus 2, 3. So this would be 25 out of 4 minus 6. The LCM, of course, is 4. And this is 25 minus 24, which is 1 out of 4. 1 out of 4. Which is 1 out of 4. So that is our x3. You now use that x3 to get y3. And y3 is given by gradient x1 minus x2, x3 minus y1. And our gradient, we had obtained 5 out of 2. x1 is our 3. x3, we've just obtained a quarter. Then minus y1, which is 4. So this will be same as 5 out of 2. And this, the bracket here has 2 3/4. When you subtract a quarter from 3, get 2 3/4, which of course is the same as 11 out of 4. 11 out of 4. The result, we subtract 4 out of it. So when you multiply this, you would have 55 out of 8. Then you subtract 4 out of 1. The LCM is 8. And this will be the same as 55 minus 32, which comes to this. 23 out of 8. Okay, that's how you do this. Now I want to look at a program to do the same. Say that the following Rust program demonstrates basic elliptic curve arithmetic on real numbers. So what it will be doing, it will be doing point addition. If points are distinct, if the points that were given are different, then it's supposed to add. It will also be doing point doubling, where you have a point added to itself, then this is supposed to do it. This is where it begins. Function add points. Add points. So P and Q. This is where 2 points are different. And I'm doing it 64 bits. Just a minute. Now, so where the 2 points are different, then this is what it's doing. What is it's doing? Now, so if the value of P, the value of X for point P and the value of X for point y are equal, and also if the y values are equal, it has said, okay, this is what I'm referring to. If x for p and x for near equal, then there'll be no result at this point. This is not doing point doubling. This one is supposed to do for when the points are not the same. When the points. Now, what happens? For instance, let's look at an example. Let me just what about if I have something like this? Just before we go on with this. What about if I have this? And then I have you see, this is not the same point, and they don't lie on the same vertical line. They don't lie on the same vertical line. So in this case, just a minute. Yes. In this case, we'll get, it will give us a result. In this case, it will give us a result. But now when the y values are the same, then another formula has to come in. The one we already talked about, because that is not always when the y values are the same. Not when y values are the same. Let me clarify here. We use point doubling where, for instance, we have 7, 4, and 7, 4. This is the same point. This is the same point. X and x are equal, and y are equal. So if x and x are equal and y are equal, then it means what we can do here is point doubling. What we can do there is point doubling. It means we will use a formula for point doubling. But look at this. If P has 7, 4, and Q has 6, 4, you notice that the x values are not equal, but the y values are equal, meaning that these two lines lie on the same vertical line. So if the vertical line is that, one point, okay, let me talk of the x-axis and y-axis. So let me say this is 6, and this is 7, and this is 4. What are you talking about here? Is okay. What is 7, 4? 7, 4 is here, and 6, 4. Oh, these ones lie on the same horizontal line. These ones lie on the same horizontal line. So these ones, we can get the sum. We can get the sum of this. Where the problem is where they lie on the same vertical line. For instance, supposing I had 6, 6, 3. 3 is here. So for instance, if n is 6, 3, n is 6, 3. So 6, 3 is here, and p is here. So our n is here, and our p is here. So these ones, the sum of this is infinity. The sum of this, when they lie on the same, but this one, that lie on the same horizontal line, this one you can add using the formula we just talked about. The formula, these are two different points you can add using that formula. Now, so we can now go back to this. So what does this say? What this one is saying is that you're given 2 points P and Q. If the x value of P and the y value of Q is the same, and also the y value of P and the y value of Q is the same, then it means that this is the same point. P and Q is the same point. So if you were to add, then what should come out should be the double point. That's what should come out, the double point. Now, what about it's only x value and y value that are equal? If it's only x value and y value that are equal, then it returns none, to mean this point is on the same vertical line. And therefore, what we then interpret is that it has given us point at infinity, the point at infinity. So that's what I was saying that supposing this is a y-axis and x-axis, and this is the value x is equals to 2, and you have a point here, another point here. And it's only x values that are equal, regardless of what the y values are. Then what the sum will be, the sum of those 2 points will be infinite. So it's supposed to return none. Now, so that is what this first part does. Then we have the part for determining the point inverse, and we already talked of that. We already said yesterday, for instance, that if you have a point 3, 4, then the inverse of this point, which we abbreviate as negative p, would be given by 3, negative 4. That's the inverse of that point. No. This I added this one here. I added this one here just to explain this. It was explaining this. These additional notes. It was just to explain this. That if points are on the same line, vertical line, then they are inverses of each other. Then the result is point at infinity. So you return none. So this was an explanation for that. It has nothing to do with what follows it. It's an explanation for the none above, return none. Now, so you have this other part. This other part now is where you're getting the gradient. Change in y, the y of q minus y of p minus x of q over x of p. So this is giving us our s. Then after getting this s, supposing that the points were different, what is x3? X3 will be, now I call lambda. Lambda is my gradient, not s. I've used lambda. I didn't use s here. Now, so what about x3? X3 will now be the gradient, which you call lambda, but now squared. So it will be lambda square minus x value of p, which we call x1 minus x2, of course, that's what we used. But it's just, this is a coordinate of p and this is a coordinate of q. That's what the formula is talking about. What about y3? Y3 will be lambda multiplied by x1 minus x3, then minus y1. So if x was the point of p, then y will also be point of p. That is what the formula says. And then after that, the formula, if that point exists, then it will just say that the result is some point x3, then y3. where x3 is the x value and y3 is the y value. That is, if the points were different. If the points were different, then this is how we'll be doing the summing, the summation of those 2 points. Let me just come back and again look at what is happening just from the start again. The points are different. They've been given point P and point Q. And I begin by looking at it, supposing that this value and this value were the same. Supposing this were the same. The x value for P and x value for Q were the same. And then you proceed and find that y values were also the same. Then it means we are doing doubling. That's we are doubling. Is that okay? That is what this one is saying. Now it proceeds and says, supposing that we have the x value being the same, for instance, this, and the y value, x value being the same, but y values might be different. Y values might be different. It means these 2 points are on the same vertical line, and therefore it will return none. What we will realize is that when you are drawing these elliptic curves and you find points on the same vertical line, what I've written here cannot be correct. What I've written here cannot be correct. What I've written here cannot be correct. For this reason, once we have this, if you have this point and this point, there can only be 2 points on the same vertical line. There can only be 2 points on the same vertical line. And therefore, those 2 points are inverses of each other. So what I expect this is to be is that this is 3, 5, then this should be 3, -5. -5. They are inverses of each other. There can never be 3 points. Look at, like for instance here, if this is a vertical line, you can only have a point here and a point here on the curve. In between, there's no curve, so there's no point. The curve is this. This is the curve we are talking about. The elliptic curve. This is the elliptic curve. Inside here, there are no points. The points only lie on the curve. So there can only be 2 points. So if this is a point, then this is another point. They are inverses of each other. And that's what I explained. That's what I was explaining at this point. That's what I was explaining. And if they're inverse of each other, their sum always will be the point at infinity. Their sum always will be point at infinity, which we abbreviated as that. And of course, we said we can also just write it like that. Supposing there's a point here, there can only be another point here on the same vertical line. So they're inverse of each other. That's a point I just wanted to emphasize again before we proceed, so that you understand what an elliptic curve is. The elliptic curve is just this curve. If we have a vertical line, only 2 points are on that vertical line, only 2 points. And they're therefore inverses of each other. So that is what we are saying here. Now, so if you discover that x value is the same, x value is the same, then it means that those points are on the same vertical line. Therefore, they'll be inverse of each other, and therefore, the result will be infinite. The result will be infinite or none. Now, what about if it's the same point? So you entered and the program discovers that this is the same point. So the program will be doing point doubling. Doing point doubling. It has begun by something here. And it's saying that if the y value is 0, let's see, for instance, you have a point like 3, 0. And you have a point like 3, 3, 0. You want to sum this. What would be the result? What will be the result? The result will be infinite. The result will be infinite. The y value is the same. The x value is the same. So it's on the same, this point. Oh, let me even say that the x value, let the x value be different. No, if the x value is different, that's a different. But you're looking at the same point. You're looking at the same point. If the y values are the same, then automatically, no, the y values, if the y values are 0, if the y values are 0, then automatically this will give you a point at infinity. If the y values are 0, because look at our formula. Our formula was 3x squared. 3x squared plus a out of 2y. And y is 0 now. Y is 0. So we're already getting a point at infinity. Our gradient is already, does not exist. Now, what about, that is a case when the y value is the same. Now, if the y value is not the same, it's not, oh, no. That is a case when the y value is 0. But when the y value is not 0, when y value is not 0, then you proceed with this formula. When y value is not 0, but when y value is 0, you don't need this formula, because this formula will not give you anything. Look at this. Look at this. This formula will not give you anything if the y value is 0, because you'll be doing division by 0, which is not possible. And so when the y value is 0, we know the result to be point at infinity. You don't need to waste time adding that. The only thing you can waste time adding is when the y value is not 0. When the y value is not 0, the formula becomes lambda, our gradient, is equals 3, the x value of p square, the x value of p square plus a out of, there's this out of 2 multiplied by the y value of p. This is the formula we're talking about. That's the formula we're talking about. And that is how we get the gradient lambda. After obtaining that gradient, now obtain x3. And x3, our formula says, the gradient square, lambda square, minus 2x, x value of p. This gives you x3. What about y3? Y3 will be gradient lambda into bracket, the x value of p minus the 3y3 that we just obtained from here. Then the result subtracted from it, the y value of p. So that is and when that happens, you now come up with a point that has x3, y3, where x3 is the x value and y3 is the y value. So that is how this program then runs. So this program is then able to give you the sum of 2 points. And those 2 points must be on the curve. Must be on the curve. But if they're not on the curve, then it will tell you that those points are not on the curve. It cannot add them. So this is then the main function, and this is why you're putting, I had included a b, but I know that this b is not used in the end of the method. in any of the methods, in any of the methods. And so you can see in my program, I've put underscore B, underscore B. So this underscore, it means I'll not use it. B is not used. If I remove this underscore, then the program will not run, or it will run with errors, because it will tell me that this B is not being used. So I put underscore so that I suppress it so that otherwise the program will request that my formulas are not using it. And of course, none of my formulas is supposed to use this B. The first formula is just using, for instance, where I'm doing doubling, I'm using S into, what was it, X1 minus X3 minus Y1. So there's nowhere I've used B, but where am I using A? Where I'm using A is the gradient, 3x1 square plus A out of 2y. So there's nowhere my formula requires B. So, but I had to state it. I had to state it so that the program knows what my equation, what my elliptic curve is. So for instance, I want my elliptic curve to be y square is, x cubed minus 4x and then plus 9. That's how I want it. So I want the program to understand my curve, but I'm not going to use B anywhere. So you cannot put something that you cannot use. The program will be asking for you to use it. Now, so that is how my program will be working. So I've then said that I want to add P and Q, and my P is 2, 3, and my Q is 0, -3. I want to add these 2 points. Then I begin by match add points. So this match add points, first of all, is determining if these points are on the curve, because you can be giving it points that are not on the curve and asking it to add. So it begins by, first of all, identifying whether these points are on the curve. And if they're on the curve, then it begins to do what you've asked it. So it will be printing what you've asked it to do. Prints none if the point is at infinity. If the point is at infinity, prints none. If the point is not at infinity, it gives you the sum. And then gives you 2p if you wanted to get 2p. If 2p is also on a point at infinity, it says that. It says that this is a point at infinity. Let me share the code that will look at how it works. Okay, this is the code. Is it this one? Okay, yes. Okay, it's this one. I've only changed the values. Okay, let me run and see. Now it has told me P1 is on the curve. P2 is on the curve, and therefore their sum is here. And if I want to get 2P1, the result will be this. So this way I defined the P1, I defined the P2, then I gave it A to be 4, A to be 4, then my P, that is the prime number, 313. And then my first point, my second point, and so on. Okay, so it has given me the sum of that. It has given me the sum of that. But that is that one I've done using mod P, but the one I wanted to share is the one that does not use mod P, because yes, the one I wanted to share is the one I was explaining. Is not the one I've shared actually. They're doing the same thing, but the one I just shared is doing it mod P. It's this one. This one is the one I'd already shared. So I'm looking for the other one. Yeah, it's this. This is the one I was explaining, yes. The one I'm doing the real numbers. So the problem there, I have so many here, so choosing which one. And they almost have the same names when I was saving them. Now, let me run this. Okay. It has given the result of P plus Q as these points. Then it has told me that if I want to add 2 to itself, to P to itself, this is then what I will get. That's what I will get. Now this, we are dealing with the real numbers, so that's why you can see this number as decimals. But this one, I was dealing with the real numbers because I want to begin looking at mod P. But this is what I was saying, that P has not been used. P has not been used. So when you don't use it, you must then put the underscore. Otherwise, it will then give you, it will ask for it to be used. For instance, if I was to remove this underscore, let's see what it says. Because my formula does not require it. None of the formulas I've given requires the use of B. Let me see what it then says if without that underscore. Yeah, it has given me some, it has run, yes, because the code is correct, but then there's some warning. And the warning says, unused variable B, unused variable B. So it means B has not been used. So the procedure will be, if it's not used, you either put underscore or you remove it. But I didn't want to remove it, because if I remove it, then it will still give me the same result, because what I require just requires let me just remove it and see what happens. Just remove it. Just see this thing is a good thing you do, you try and see what happens, and then you just return. Yeah, when I remove it, it just runs. B was not required here. B was not required, but I just put because I wanted to just have a complete elliptic curve, but B is not required. It's not used in any of my examples or formulas. So you may not require it. Okay. So you know what debugging is. Debugging is this one, just using it. If you want it to, for instance, when I was doing this program, I discovered it was not giving me the exact results that I was getting on manual calculation. So when I'm doing manual calculation, it was not giving me the same results. So what then happens, you want to debug and see where the problem is. So that when you debug, it runs every step. It runs every step and gives you the result for every step. So for instance, when it's getting the gradient, it will give me the point for the gradient. Just tell it print lambda, then it prints for you lambda. You tell it print this. So I wanted to print every step so that then I compare every step with my manual calculation and see where the problem is so that I can rectify that. So that's what we call debugging. Debugging, then you ask it to print every step, then it will be doing that. So then you want to compare these steps, each one of them to your steps. Because I was doing it manually and then first before I do the program. Okay, I just want to show a few examples and then we'll stop there. No, actually, it's not a few examples. I think I've exhausted what I was to teach today. If I say I go to the next topic, you guys will be tired if I am done with it. So I want to stop there so that then we meet next time to look at elliptic curves mode P. And this is what we want most. And of course, we'll just be doing addition of points the same way we've done, the same formulas. So the introduction we've done, and you remember this discriminant, again, it will be telling us that this is an elliptic curve or not, and so on. That discriminant, we talked about it last time. So that's what we'll be doing. We'll be just doing the same thing we've done for integers, generally. So now, with that knowledge, we will now narrow into mod P. So we do summation, mod P, and so on. So that one is for Friday. Thank you.